So we're going to look a little bit closer at single displacement reactions. And we've kind of been programmed to think that if we write a few reactants together in an arrow, that something always has to happen. And we're just going to see kind of why things do happen that way sometimes, and other times maybe no reaction actually does occur. And what we're going to use to help us figure that one out is something called the activity series. So the activity series, and we'll see what it looks like on the next page, is a chart of most metals on this one, and we'll see a second one for halogens, with the most reactive metals listed at the top, and they'll become lesser and lesser reactive as we get to the bottom. So if you have a reaction that involves an extremely reactive metal on its own as the element and a lesser reactive metal within the compound, this more reactive metal has the ability to kick the less reactive metal out of the compound and make a reaction occur. So let's just check lithium and sodium. We'll go to this table. There's lithium at the very top. It's most reactive, and sodium is still quite close to the top. The only important thing is that it's lower than lithium. So whatever is the top metal, lithium in this case, is going to be the one that's found in the compound in the end. So it's more reactive, it will displace sodium and become lithium chloride and sodium as a solid metal. This is a single displacement reaction. We have a second one, SN, tin, and magnesium. If we go to our table, we have magnesium right here, and we have to find tin, which is much further down. So magnesium is the more reactive metal. It's going to be the one that's in the compound. So we have, I've gone too far, I'm sorry. We've got magnesium. Right now it's not part of the compound, so it's going to kick tin out and end up bonding up with the carbonate, and tin will be all on its own. Again, when we were talking about reactions before, when we write our products, we need to make sure that they're still balanced, right? So lithium's charge would have been a 1 plus, chlorine's charge a 1 minus. That's why we have no numbers. It's nice, everything doesn't have a number, it's completely balanced on its own. Magnesium is in column 2, it'd be a 2 plus charge. Carbonate, you might be looking into a table that we had a couple lessons ago. So 2 minus, the 2 and the 2 minus get swapped and cancel out because they're both the same number. This must have also been a tin 2 as well to not have a number, right? Which is nice. No need to balance. So these have both been examples where the lone element has been higher on the activity series. But of course, it's also possible that you just mix two things and the lone element is lower on the table. So those will be your favorite reactions because they don't react, but you still have to make it look like you did the question, right? You didn't leave it blank. So if that were to happen, on the other side of the arrow, instead of writing any products, we're going to write no reaction, or even quicker NR for no reaction. So let's just double check. We've got AU, so gold, mixing with hydrochloric acid. So it's going to possibly swap places with the H, right? AU is a metal, it'd have to be at the front of the name. So let's check for gold and hydrogen on the activity series. So still scrolling, haven't seen either. There's hydrogen. It's pretty low, but gold is the lowest. So no matter what, gold doesn't have the ability to push hydrogen out of the bonds it has in that compound. So higher hydrogen, hydrogen's going to be part of the compound. So it already is part of the compound. There's no reason to write all this stuff back over here, making it look like something happened when nothing did. It's like plopping a gold necklace just into acid. and watching nothing happen. So we want to make sure it's obvious that nothing happened by writing no reaction, which makes sense that gold's at the bottom, right? And a lot of gold jewelry you can pass on from generation to generation, and it still looks just as nice as long as you keep it clean. Obviously, it doesn't react in order to be able to have that longevity. Let's see, copper, and we already know lithium's the very top thing, so no matter where copper is, it obviously can't replace lithium in this compound. So let's check. We have copper being right here. Okay, so copper is kind of near the bottom. You can see that like all the jewelry metals are pretty much near the bottom, except for mercury. So copper, again, on its own at the end, because lithium is the higher on the table. We're not going to rewrite all of this because then it makes it look, if you quickly look at this, like a reaction did happen. So instead, NR or no reaction. And this is a very outdated example, but pennies won't decay in a base. That OH means it's a base, but pennies haven't been around for a while. So activity series usually look at metals, so the front stuff of a compound or a lone element. There's also the possibility of stuff at the back of your compound, or now a molecule as well, switching, which is the activity series of halogens. So if we're switching a diatomic molecule, it would be with any of these letters, these elements, fluorine, chlorine, bromine, and iodine. It works the same way. So if you're at the top, fluorine is the most reactive. It is going to always, always, always be in a compound or a molecule if it can be. There's no way that iodine could kick it out. Chlorine being the second most. It cannot kick out fluorine, but it could kick out bromine and iodine, and so on. So that's just looking a little bit closer at single displacement reactions and seeing that just because there's a reaction written on paper, it doesn't always have to happen. And it's based on these rules. So let's just see one that hasn't been done for us, because it's always a little bit different that way, and see what we're doing. So let's see. We also have to balance. So we've got copper and silver. We don't care about this nitrate yet. It'll help us when we come to balancing, but we just want to go to the table and look at copper and silver. Whichever one is higher up will be paired with nitrate. Lots of scanning. We've got copper and we've got silver. So copper is going to be part of that compound. Is it already? Let's see. It is not. So we're going to have a reaction. We're going to have silver written all on its own, Ag solid. That's easy, right? It's off on its own. We don't have to worry about kind of what subscripts it's going to have, what numbers. Copper and nitrate are going to be together. So the nice part about this is we know that copper can have two different charges, right? Let's make a charge that works best for us. If we want to make it a copper 2 or a copper 3, that's up to you. But I mean, when we go further down, perhaps you can pick something that doesn't lead to you balancing too much. So you could pick a copper 2+ or 3+. I'm just going to pick 2 because it's lower. I'm going to crisscross it with NO3. NO3 has a charge of 1-, so there's no number to really crisscross with it. So we'd have our Ag solid plus Cu, and then in brackets, NO3, 2. Then we have to balance that. I'm not going to do that here just because I can't see anything and it's actually going to make it too hard on me. There's a few of these that are no reaction, not a ton, but a few of them. And then there are a couple of these that have F2 and Br2. So those are our diatomics that are going to use that activity series for halogens. So that F2 and that Cl might or might not end up reacting and switching spots, and that Br2 and that I2 might as well.